All right, last one is exponential and log equations that you have to be able to solve. And you, again, done this before as well. So we will solve some exponential and logarithmic equations. And that should finish up your stuff on this. So we'll start with, and this is section 3.4 in your textbook. So we'll start with exponential equations. So like, let's say you wanted to solve something like 2 to the x equals 32. You may or may not need to use a log to solve it. In this case, you can probably visually figure out 2 to what power gives me 32. But one of the ways that you can do it is you can change the bases and make them the same. So I can think of like 32 as 2 to some power. So 2 to the 5th power would give me a 32. And so then once the bases are equal, then you just say, well, whatever's in the exponent spot has to be equal. So x should be 5. But that one you would have been able to solve probably just by looking at it, because you know that 2 to the 5th power would be 32. They can get more complicated though. So you could get something like maybe 1/3 to the x power equals 9. So it might be a little bit harder to figure out what the exponent would have to be in this scenario. So I'm going to do that same thing. I'm going to try and make the bases the same. So the 1/3, I'm going to change that to be 3 to the -1, because that is the same as 1/3. And then 9, I'm going to rewrite as 3 to the 2nd power. So I'm trying to make the bases the same if I can. And then the property on a power raised to a power, those 3 to the -1 raised to the x, you would multiply those together. And as soon as I've got the bases totally the same, I can say, oh, well, I'll just set the exponents equal, because if the bases are the same, then the exponents have to be the same, which means that the exponent x should have been -2. Again, that one's still pretty straightforward. Sometimes you'll get equations that you can't necessarily do that to. So like, what if I had ended up with something like e to the x equals 7? Well, e is such a special number, like you cannot rewrite 7 to be in terms of e. So in this scenario, I'm going to do something to both sides. And in this case, I'm going to take the log. I'm going to take the log of both sides. This is one way to do it. And I'm going to make the base match the base of that guy there. So I'm going to take the log base e of e to the x, and I'm going to take the log base e of 7. Now the reason why I wrote it out is because remember, when the base of the log and the thing that's inside the log are the same, they, or you can, use your property of bringing this into the front, and you'd have x times the log base e of e. And anytime the base and the number inside the log are the same, they just reduce out to 1. But really what I would have done was I would have write this as the natural log. I don't ever write log base e, because it's not necessary. So this will just be 1, so you'll have x, which is equal to the natural log of 7. That's one way to do it. And then whatever that's a decimal, obviously. Another way that you could have done it, so we'll say or. In the very beginning, you had e to the x equals 7. You could have said, hey, Miss Griffith, remember, a log is an exponent and a base is always a base. Hey. That's what we talked about before, right? So you could have said, hey, a log is an exponent. That just means a log is equal to an exponent, and a base is always a base. Well, the base of the exponent of the exponential piece is e, so that'll be the base of the log, and then the 7 will go inside. And then I've gone straight from the problem to the answer. So remember, log base e is really natural log. Same answer, just different approach. Both are useful. I'll be doing both ways. All right, so what about if I have something like e to the -x squared equals e to the -3x minus 4. Okay, well, this is very straightforward. I've got, you're solving for x, but you've got a base is the same. So I'm just going to go ahead and say, all right, base is the same. That means that the exponents have to be the same. So as soon as I set the exponents equal to each other, I realize that I've got now a quadratic equation. So you have to remember how to solve a quadratic equation. You'd want to set it equal to 0. I'm just going to move the x squared to the right because that's faster. Plus, I like having the leading coefficient positive. Then if you can factor, we should go ahead and factor this. So this will be x minus 4, x plus 1, and then set each of those factors equal to 0. So x minus 4 equals 0, x plus 1 equals 0. So x is either going to be 4 or x is going to be negative 1. And really, either one of those would work because if you were to plug them into the original problem, they would both give you a true statement. So if I were to check, which is really easy to do, you'd have e to the negative 4 squared equals e to the negative 3 times 4 minus 4. This will be e to the negative 16, which equals e to the negative 12 minus 4, which is also e to the negative 16. And then if I plugged in negative 1, e to the negative 1 squared. Sorry, I messed up. It's supposed to be e to the negative 1 squared equals e to the negative 3 times negative 1 minus 4. So this will be e to the negative 1, e to the 3 minus 4 also checks out. Okay. Well, when we're solving log equations, that's it's important to do the check. That's why I walked you through it. But exponential equations, remember that exponential functions of the domain is all real. You can plug anything into an exponent, doesn't matter. So really, exponential equations aren't as important to check, but good to start practicing. Okay, I can do 3 times 2 to the x equals 42. So first thing I'll do is divide both sides by 3. And that'll give me 2 to the x equals 14. If I can make the bases the same, I would do that, but I don't, there's like 2 raised to a power does not give me 14. So one of 2 ways, either take the log of both sides and make the base the same as the base that we have, which is what I'm going to do. So I'm going to go ahead and take the log of both sides, but I'm going to choose to do it with a base of 2. And the reason why I'm choosing to do it with a base of 2 is because of the fact that the exponent is on a base of 2, so it's 2 to the x. That x can be moved into the front, so now I've got x times log base 2 of 2 equals log base 2 of 14. And then remember, whenever the base and the thing inside of it match, that's just 1, so x times 1. And I'm just going to stop there. I don't, unless you want to type in your calculator, you can, but whatever that would come out to be equal to. It's about 3.807. Other way you could have done it, so, or instead of taking the log of both sides, right here, when I had 2 to the x equals 14, you could just say, hey, Miss Griffith, you always say a log is an exponent, a base is always a base, hey. So I agree, a log is always equal to whatever the exponent is, and the base is always the base, and then you go straight to the answer when you do that. Again, totally up to you. All right, let's do one where we could use our calculator. I'll do it with and without, like we'll do it both ways. So we'll have, we're going to solve e to the x plus a 5 equals 60. So doing it without the calculator, the first thing you need to know is that before I can say a log is an exponent, a base always, but you have to get that log by itself first. So no matter what you're going to do, you do need to subtract this 5. So we'd have e to the x equals 55. And then again, there's 2 ways that you could go about with this. We could take the log both sides, which I'm going to do. I'm going to take the log. This time I'm going to do it with a base of e. So rather than writing log with the base of e, I'm going to choose to do natural log. So I'm going to do the natural log of the left side and the natural log of the right side. And then that means that the left side, remember the base of a natural log is e, so that'll just become x. And this will just be the natural log of 55. And that would be my answer, whatever decimal that comes out to be. Again, or right here, when you were at e to the x equals 55, you could have said, hey, a log is an exponent, a base is always a base. So a log is always equal to the exponent. The base is e, so that'll be the base of my log, and whatever else I've got goes inside, which means that really I've got the natural log of 55 equals x. Keep changing colors up on you. I don't know what colors I like to use. All right, let's use the graphing calculator just for fun. So I'm going to be in my graphing calculator, and I'm going to, first of all, get my decimal to this. So the natural log of 55, that puts me at approximately 4.007. Okay, so that's my answer. So I'm going to approach this problem just slightly different, just to remind you that there's other ways to do these problems. I'm going to use my graphing capabilities, and I'm going to type e to the x plus 5 into y1, and I'm going to type 60 into y2. So grab your calculator and type in e to the x plus 5 into y1, and then 60 into y2. All right, if you've done that, then we want to graph basically where these two graphs intersect, because the question was e to the x plus 5 equals 60. So really what I'm asking you is, where do these two things intersect? So before I do that, if I just were to be in a Zoom standard window, which is probably what I'm already in, which goes from -10 to 10, -10 to 10, x and y, I won't be able to see my whole picture. So I need to remember that this y value is up at a y value of 60. So I'm going to come over to my window first, and I'm going to make my y maximum something bigger than 60. So maybe I'll change this to like, I don't know, 75 or 80, something like that. And then I hate it when the scale, like, it's gonna put actually 85 tick marks, because it's gonna go from -10 to 0 and then up to 75. So I don't want 85 marks. So maybe I'll change my scale to go like every 10 units instead of, that's just because I don't like it when it gets messy. All right, hit graph. I'm waiting for these two guys, if they'll intersect here. Boom, there it goes. Exponential functions grow very, very quickly. Just like that COVID-19 apparently seemed to grow quickly. It was growing exponentially. We wanted to like get that curve to level off and flatten back out. That's actually called a logistic curve. So I just want to find that intersection point. So I'm going to go to calculate, which is right above trace. So I'm going to go second, calculate. I'm going to go down to number 5, which is the intersection. It's going to ask you those 3 questions. First curve, you just hit enter because you're on the exponential function. Second curve is that y equals 60. When you're going to take a guess, if you want to move your cursor over there, you can, but we only have the one intersection point, so we don't have to. And there's that value, 4.007. Now, the only bad thing about this is the calculator will not tell you that the answer was the natural log of 55. So there's no way to know that that would have been the answer, but it's just another way to get that approximation. Okay, so your turn. Let's do e to the x minus 7 equals 23. And I want you to, the answer choices are going to be exact values. So you can use your calculator if you want, but the answer choices are going to be exact values. All right, did you get it? I hope so. So first thing you should have done was move the 7 over. So e to the x equals 30. Take the natural log of both sides. So when you do that, that'll give you the natural log of e to the x equals the natural log of 30, which means that x equals the natural log of 30, which is what you should have gotten as your answer choice. But if you put that into your calculator, that was approximately 3.401. Or if you graph it on your calculator, the intersection point between the two, same value. All right, so now we're going to solve this one. And again, if you really wanted to, you could put all of this left side into y1 put this right side into y2, and you can calculate the intersection point. So those are important things to remember. Even when you're in calculus, you can always, if you're allowed to use your calculator, this is one easy way to solve an equation. Just type one side into y1, type the other side into y2, and figure out where they intersect. I'm going to go through the algebra on it because it's not always going to be a calculator question. So the first thing you need to do is you need to isolate whatever is the exponential piece. So the 2x minus 5 is only raised to the 3. So this is the thing that needs to be isolated. So you're going to add the 4 and then divide by the 2. All right, add the 4 and then divide by the 2. I'm just going to leave it as a fraction because I am. All right, then from there, you can go through by saying a log is an exponent and a base is always a base, or you could take the log of both sides. In this scenario, I would do the log of base 3. So I'm going to do the log base 3 of the left side. And I'm going to move this equal over so I can have a little more room. And I'm going to do the log base 3 of the right side. So when you do that, the left side will become just 2x minus 5. And the right side will be log base 3 of 15 over 2. Okay, we got to finish solving for x. So I'm going to add 5 and divide by 2. So you'll get log base 3, 15 over 2 plus a 5. And then all of that will be divided by 2. So your final answer would be log base 3 of 15 over 2 plus 5, all of that divided by 2. Now that would come out to have been, if you typed it into your calculator, approximately 3.417. But again, if it was a non-calculator question, which of course for you guys, you'll have your calculator the whole time, but if it was a non-calculator question, you might not have been able to just graph it in your calculator and go from there. All right, your turn. Solve 6 times 2 to the t plus 5 plus 4 equals 11. Alrighty, how'd you do? First thing you should have done was to subtract the 4, then divide by the 6. So that would give you here. Then I'm going to take the log with a base of 2 of both sides. So log base 2. That'll make the left side become just t plus 5. And the right side will be log base 2 of 6 over 7. And then I'm going to subtract the 5. So log base 2 of 6 over 7. And then minus 5. If you had done it on your calculator, you would have come out with approximately negative 4.778. All right, on to logarithmic equations now. Okay, so we're going to solve a log equation. So remember, with exponential equations, the domain on the exponential functions is always all real numbers. So any solution you get, if you're solving an exponential equation, any solution you get is an okay solution to hold on to, because the domain is all reals. I mean, unless you made a mistake and then it's just a wrong number. But for logarithmic equations, you have to be careful because the domain is the range from the exponential. So the exponential functions only had a range that was positive numbers. So the domain of a log is only positive numbers. So you have to be careful with that. So we'll start simple. Say I'm solving the natural log of x equals 2. Well, the easiest way to do that is to say, all right, a log is an exponent, a base is always a base. So I could just rewrite it by doing the base is e. And if a log is equal to an exponent, then 2 is the exponent and the base would be e. That's one way to do it. Or if you've got the natural log of x equals 2, then the base is e. So what I'm going to do is I'm going to make both sides be an exponent. So I'm going to have this be, and I'm going to choose the base of e that I would have had here. So I'm going to make them be exponents, and the base is going to be an e. So I'm going to do e raised to the natural log of x equals, and then e raised to the second power. So basically I'm making the natural log of x and the two be exponents, which is fine. It's still an equivalent statement because I basically just know that those exponents have to be equal. And then from there, the left-hand side, because the base of the log is the same as the base of the exponent, that just is going to be e, or excuse me, x. So either way, your answer would just be whatever e squared is. Always, fallback is you could have typed the natural log of x into y1. You could have typed 2 into y2 and solved from there. Alrighty, still keep it simple. What if I had log base 3 of 5x minus 1 equals log base 3 of x plus 7? Oh, and I forgot to talk about, real quick, this is a positive number. So because e squared is positive, I know that would have been an okay number to have had in my problem, because inside of a log has to always be a positive number. Okay, on this one, they're both log with base of 3s. So just kind of like when I made the bases the same on the exponentials, I'm going to do the same thing here. So if they're both, log base 3 of something, then the things inside, the somethings inside have to be the same. So the 5x minus 1 better be the same as the x plus the 7. So then I am going to get 4x equals 8, which means that x equals 2. Now I do realize that 2 is a positive number, but you have to make sure that when you plug it in here and here, you get true statements. So this would be what? 10 minus 1, which is 9. This would be 7 plus 2, which is 9. Yeah, we're fine. Because remember, whatever's inside of a log has to be a positive number. You can't ever get a negative. Okay, let's do log of 4x minus the log of 12 plus x equals the log of 2. Okay, before you solve this one, you will need to condense these two logs together. All right, how'd you do? Hopefully you condense those together. They all have the same base. They're all base 10s, so I can condense that through division. That was in your previous video. So that'll be the log of 4x over 12 plus x. And again, now that their logs are both set equal to each other, I can just take whatever's inside the logs and set them equal to each other. And then it's just a problem I have to solve. I can multiply both sides by 12 plus x. And I'm just chucking along here, assuming you don't have problems with these kind of equations. Okay, so I got x equals 12. Again, before I totally take that and run with it, I just need to make sure that I don't get any issues with what's inside my log, because again, inside of a log has to be a positive number. So if I plug the 12 in here, that would be 4 times 12 is 48, no problems. Plug the 12 in here, 12 plus 12 is 24, no problems. Well, that's just a 2. So no problems there. So we're good. We can keep x equals 12 as my answer. I just realized that you guys didn't hear any of that I just said. So here's my next problem that I was working with you guys on. 5 plus 2 natural log of x equals 4. The first thing I did was I got the natural log of x by itself. So that's how I got down to the natural log of x equals -1/2. I did the rule where if the base is of the natural log is e, I made them both into exponents. So e raised to the natural log of x, and then e raised to the -1/2. And then anytime it's e raised to a log that has the same base, that'll just be an x. E to the -1/2 is not negative. It's really 1 over e to the 1/2. We get about 0.607. So that's how I solved this equation. I'm about to take the second approach where I then type 5 plus 2 natural log of x into y1, and I'm going to type in 4 into y2, and then I'm going to graph these two and find the intersection point. That's where I'm heading. So into y1, type in 5 plus 2 ln of x, and then into y2, type in 4. And then you actually probably could do this one in a standard window because negative 10 to 10 would find that value of 4. So I'm going to have my window in a standard window, and it looks something like this. It does keep going. Like, there is still more values down here, but the calculator can only graph functions. So if it gets too vertical, sometimes it struggles with the pixels. So even though it doesn't look like it keeps continuing, remember, logarithmic functions are going to have a vertical asymptote. So it does keep going. I'm going to calculate that intersection point. The first curve, I do want to make sure that I'm on that first curve. So there we go. Now I'm on the first curve. Okay, so be on that first curve, second curve, and then the guess. And look, there it was. 0.607 is what I had rounded mine to. But again, unless you had done it by hand, you would not have gotten that it was 1 over e to the 1/2. All right, next one is for you to do. And you'll have to do it by hand if you want the answers to match up to what they've got, or you can always take the answer choices and evaluate them. All right, did you get it? All right, so first thing is subtract the 7 and divide by the 3. Whoops, I'm not sure why that did that. Subtract the 7, divide by the 3, so that'll be the natural log of x equals negative 2 over 3. Remember, logs can be equal to negative numbers. Then exponentiate both sides. So when I do that, it would be e raised to the natural log of x and e raised to the negative 2/3, which means that I would have x equals e to the negative 2/3, which is not a negative number. It's really 1 over e to the positive 2/3, which would have been approximately 0.513. All right. So now we're still talking about this whole, you've got to make sure that what you get inside of a log is always a positive number, because there are times when those things will give you answers that maybe you can't actually choose. So let's walk through one right now. We call those extraneous solutions. And I know this is all review, so it might be a little bit boring for some of you guys that have real great retention, but this is something that people forget all the time. So I would say that most of you guys have probably forgotten some of this stuff, and this is a good review. All right, so before I do this one, I do want to condense those two logs into one. So because they both have the same base, and because they both have base, and because they're their addition, I'm going to condense that into one log, and I'm going to do that through multiplication. So that'll be 5x times the x minus 1. All right, then from here, you can decide how you want to deal with this. So I can either say a log is an exponent and a base is always a base. So if I do that, then I would say that the log equals the exponent. So 2 is the exponent. The base, which isn't written, is 10. And that'll be equal to the 5x times the x minus 1. Okay, so that's one way to do it. I usually say, oh, the base is 10. Let me do 10 raised to both of these sides. Because then when you do that, you're going to basically cancel these out, and you're left with the 5x times the x minus 1. You get the same answer either way. Doesn't really matter. Okay, so this is a quadratic equation now. So 5x squared minus 5x equals 100. And quadratic equations have to be set equal to 0. So I would have 5x squared minus 5x minus 100 equals 0. I'm actually going to just go ahead and divide everything by 5 since, you know, I've got that ability to. And then I'm going to factor if I can, which this one looks like it's pretty easy to factor. So x minus 5, x plus 4. And then set each of the factors equal to 0. So either x minus 5 equals 0 or x plus 4 equals 0. So I get x equals 5 and I get x equals negative, oops, gosh. And I get x equals negative 4. All right, now you do have to be careful. Just because you get, remember, a negative number as an answer does not mean that it's an issue. It's just something that you have to like double check and make sure that you're good with. So I'm going to take the 5 and check it real quick, make sure it works. So if I were to plug 5 into here, this would give me the log of 25. And this would give me the log of, what, 5 minus 1, which is 4. So no issues with that one. That would be the log of 25 times 4. And that's not going to be a problem. So 5 is fine. And now I'm going to check negative 4. If I check negative 4, that's going to cause me some problems. So if I plug negative 4 into here, already that gives me a value that is negative. And inside logs, they have to stay positive. So this one is called an extraneous solution. And that just means that it's a solution that you got because you weren't solving a log equation anymore. You got to a point down here where you now had a quadratic equation. That's fine. For the quadratic equation, there was definitely 2 solutions, but the original problem wasn't a quadratic equation. It was a log equation. So you got to throw that one out. The only answer you're allowed to hold on to is the x equals 5. So be careful when you're solving log equations because you can be tricked into sometimes having an extra answer that you didn't mean to have. All right, your turn. Solve log of x plus log of x minus 9 equals 1. All right, so you should have only gotten an answer of x equals 10, but if you're not careful, you might have accidentally held on to an extraneous solution. So first thing you should have done was to condense the 2 together, so you'll have log of x times x minus 9. I usually like to do brackets to make it easier to read. And then exponentiate both sides, so that'll be 10 raised to this side and 10 raised to that side. The reason why we do that is so that those can cancel out. So we're left with x times x minus 9 equals 10. So really I have x squared minus 9x equals 10. To solve a quadratic equation, you have to set it equal to 0. That one's pretty straightforward for factoring. So x minus 10, x plus 1. So you'll get x equals 10, and you'll get x equals negative 1. Again, just because you get a negative answer does not mean that it's got to be thrown out. You just have to make sure that it doesn't allow a negative inside the log. So this one's extraneous. This one checks out. So 10 is the only answer you get. All right, I have just a couple more examples for you and then you'll be done. This one is another exponential equation. So no matter what your solution is, it's going to be fine because the domain of an exponential function is always all reals. But this one is a little bit unique. E to the 2x, that's the same thing as e to the x squared. And what I'm going to do is something a little bit unique. I'm going to pick like a different letter, like maybe I'll pick U, and I'm going to let U for just a second be equal to my e to the x. So this problem is going to actually become u squared minus 3u plus 2 equals 0. So I'm changing colors because I want you to understand that this is not the original problem. It's just I've got a little substitution over here. So I've done a substitution and basically I've made myself a quadratic equation. Variables are arbitrary, so whether this was x squared minus 3x plus 2 is no different. So I can now solve this by factoring. And this is pretty straightforward for factoring. So u minus 2 and u minus 1. And when I set each of those equal to 0, I would get u equals 2, and I would get u equals 1. But the problem's not done. So remember, we did that substitution, so really I have to go back and remind myself that really u was e to the x. So really I've got e to the x equals 2, and I've got e to the x equals 1. And so to finish solving for these, I'd have to take a log with a base of e. So really I take the natural log of both sides. So I've got the natural log of e to the x equals the natural log of 2. And natural log is really log base e, so that'll just be reducing to x. And over here, I've got the natural log of e to the x equals the natural log of 1. So again, same thing, I'll have x equals, and then the log of any base of 1, remember that one's always 0. So just kind of a unique way in how you solve this one. We'll get x equals the natural log of 2, and x equals 0, and both of those are okay answers because the domain of an exponential equation is always all reals. If you really wanted, you could have typed the natural log of 2 into your calculator and said that it's approximately 0.693. That's also okay, but not necessary. Okay, so one more for you to try on your own. Solve e to the 2x minus 7 e to the x plus 12 equals 0. All right, so that one you would have gotten 2 that were just the natural logs. So again, you would have done your substitution. You would have ended up with a u squared minus a 7u. Oops, I think it's a different color. A u squared minus a 7u plus a 12, which would have meant you would have gotten down to, I'll do it over here, u squared minus a 7u plus a 12 equals 0. You've gotten down to u minus 3 and u minus 4, which meant that you would have had u equals 3 and you would have had u equals 4. So then you would have had e to the x equals 3, and you would have had e to the x equals 4, which meant you would have had x equals the natural log of 3, and x equals the natural log of 4. Again, by the fact that the domain of exponential functions is all reals, then there wouldn't have been any need to check these, but you would have gotten, if you type it in your calculator, about 1.009 and about 1.386. All right, so with your practice that you're going to have in solving logs and exponential equations, you might end up with more like types that are funky and unique that you didn't see in the notes. So you might want to hop on Zoom on Friday or hop on Zoom one day next week to get those questions answered. Alrighty, guys, this is it. This is the last video you're going to have to watch, so isn't that awesome? All right, bye, guys.